Of course, you haven't finished all the report yet. There will be some soaking experiment, but it will be fine. The deadline for both reports will be the end of the October, so we still have enough time to work on the experiment. And also, I hope you can all try to follow the schedule as I posted it online, because we will have for the third experiment about the gyratory compaction test, we have to make an appointment with the lab technician in ADL, and it may not be easy for us to change the time. So if you have any issue before that, let me know, and I'll just try my best to accommodate all the in-person students to the lab. Okay. Okay. So that will be the lab things, and also remember that you will have one deadline for the homework 1 by the end of this week. Feel free to email me or the TA if you have any questions about the problems in the homework 1. Okay. So in the lecture today, we will continue the highway subgrade structure from last class, and last time we finished at the introduction about the different type of the compactions. We introduced the standard protocol test, which will tell you how to do the compaction for the soil samples. And usually we will do this, prepare the sample in the mold with 3 to 5 layers. And in our lab, we're doing 5 layers. And they have to, each layer will receive several number of the blows. Like typically we will apply 25 blows with a hammer as the weight of 2.5 kilogram, and the height of the drop is about 30 centimeters. This is the instrument we're going to use for the compaction. And for the mold, we have the standard size. This is the size of the mold we're going to use for the CBR test. It has the diameter of 114 millimeters, and the height of the mold is around 160 millimeter, and for the sample itself, it has the internal diameter of 101 millimeters, and for the hammer, the weight, as what we specified previously, is usually around 2.5 kilogram, and the drop is around 300 millimeters, and then for the hammer we use is 305 millimeters. The length is 305 millimeters, and you need to use this hammer to do the compaction by hand, and it takes a lot of time to prepare the sample. And there are actually some standard operations for you to do the compaction. At first, definitely you need to mix the soil or the aggregates with the water, because we usually want to test the physical property of the soil and the different water contents. And it's ideally you will be recommended to prepare several samples at the same time with different water contents and do the experiment. And of course, you need to apply the blows to the sample, and it could be 3 layers, it could be 5 layers. And this would be the figure on the left here actually shows how you're going to do the blow to the sample. Usually, you should do the 4 blows at the beginning, as was shown in the figure on the left. And then you have to do the continuous blow clockwise or counterclockwise, either way is fine, and finish all the 25 blows. With that, you will complete 1 layer and then add more materials for the next layer and so on. So this is the standard Proctor test for the preparation of the compaction samples. And Usually for the standard test, you need to estimate the dry density of the sample, and we will have to use that one by either we get the dry density from the sample you store in the oven for at least 1 day, or you can calculate them from the wet density and water contents. And this is just for the standard Proctor test. There's some other modified test, and usually this modified test is applied for the airport pavement and highway pavement, where we have the much higher load and much more frequent load. For the modified Proctor test, we have the mold size, the same mold size. The volume of the mold is 943 cubic centimeters, and but for the hammer we're going to use, it's different. Actually, you can find out this set of the hammer in the in our lab. So the height is set as 45 centimeters, and it's much heavier. So the weight of that one is around 44.5 Newton. And usually for the modified Proctor test, we would need to conduct 5 layers and also apply 25 blows for each layer. The energy would be around approximately 4 to 5 times higher than the standard test. And with that, we can with the compaction, we can actually check the changes of the properties for the soil. These two figures shows the changes of the dry density, which would be the density of the sample under different water moisture contents and different compaction levels. And the figure on top will actually shows the stress required to cause 5% strain, which is applied to measure the stiffness of the material. Basically, you can see that the with a higher compaction level, the stiffness will be larger, and also you will observe the changes in about the dry density. Usually with a higher compaction level, the dry density will also be larger, but you will observe the reductions in the for the optimal moisture contents for the sample under the under higher compaction levels. So that's the general impact of the compaction to the aggregate samples. And also there will be some different ways for you to conduct the compaction. You can use kneading, the vibratory, or some static force to do the compaction, and they will actually have different effect to the properties of the sample. For example, we can, if we go to check the shrinkage of the sample, the kneading will have the significant reductions about the volume of the sample. Especially when the water content is high, the reduction will be much larger. Followed by the vibratory method, and the static method can give you the least reduction in the or the least shrinkage of the sample. And also you can observe the changes of the density. This will actually follows the same trend from different methods, kneading, vibratory, or static. But still you will observe the concave relationship between the density and the moisture contents. With that, we can actually have a quick summary about the effect of the compaction on the soil property. First things like for the density, definitely if you increase the compaction effort, the density of the soil will be larger. So this is intuitive correct. You actually try to remove all the air voids in the sample, and the volume is reduced, but the mass is still the same. So That's the first effect. You will reduce the increase the density, and the second one, you will observe that with the higher compaction level, there would be low water contents, and you will observe that the strength will be higher, and especially the strength of the sample at the low water contents. And this can actually be, this one is quite similar to the stiffness. It will have the more capability to resist to the traffic load. And regarding to the stiffness, this is a little bit tricky. This can be the effect can be categorized under the dry of the optimal and the wet of the optimal, which would be for the dry of the optimal, it means that you do the compaction when the moisture content is less than the optimal moisture contents. The wet of the optimal indicates that the compaction is conducted when the water content is higher than the optimal moisture contents. And clearly the stiffness increases with the compaction level a lot when it's conducted under dry of the optimal. But for wet of the optimal, the situation is very different. For the wet of the optimal scenario, the stiffness will almost be the same under different compaction levels, or the changes is marginal. So usually we can see that if we want to increase the stiffness of the sample, you need to do the compaction under the dry of the optimal. But there will be some issues about the dry of the optimal scenario. And this first one is the permeability. Usually for the if you apply the higher compaction effort to the sample, the permeability of the sample will be reduced. And this is the one. This is actually quite intuitive, because we have the smaller voids in between, and it would be hard for the water to go through the sample. And the last one would be the swelling or the shrinkage potential. This is another issue for the dry of the optimal compaction. Usually for the if we conduct the compaction under the dry of the optimal, the swelling or the shrinkage potential will be larger, which means that the changes of the volume could be significant when you increase the water contents. So in reality, the most common way for us to conduct the compaction for the in situ soil or for the aggregates we want to use for the pavement design, we have to do the compaction under a little bit wetter of the optimal. With that, we can maintain a reasonable high stiffness, but we can also prevent the swelling or the shrinkage potential. So there will be, we also have some comments about the compaction. So first of all, most people just think that intuitively think that the purpose of the compaction is trying to make the density of the soil higher, but that's not true. Instead, the purpose of the compaction is to maintain a good physical property of the soil for longer time. Higher density is not our purpose. In the pavement design, it does not mean that the higher density will give you a good feature. And for the compaction, we have to consider two factors. One is the swelling potential, and the other thing is about the required density. So we just need to make sure that the density is reaching to the expected value, as well as we want to prevent the potential swelling, the swelling potentials under different water contents. And as what I just explained in the previous page, the soil is actually compacted a little bit wetter of the optimal to prevent the swelling potential. And if it's in dry of the optimal, then it will create a significant deformation for the pavement structure. Also, if there are some expensive soils in the area, you may do some cut, and if you do the cut about the expensive soil and remove them from the field, then you have to rebound the soil to make sure that they won't affect the pavement structure. And if you do some refill for the cutted area, for the cutted region, then you need to consider the settlement of those refilled material due to the potential increase of the moisture contents, and this might cause the rotting or fatigue cracking for the pavement structure. So another things like sometimes we want to minimize the impact of the moisture contents by introducing some cement or the lime, but this kind of design should be carefully considered, because the inappropriate design may induce the shrink cracks, and there will be some worse failed example in Highway 417, and there you will observe a lot of cracks on that road. And that will be the impact of the soil, of the water. And actually, we can make a simple summary about the impact of the water contents. Basically, they will reduce the stiffness and the shear strength of the soil, and increase the deformation of the soil. The deformation is usually caused by the swelling shrinkage potential. With these two changes about the soil properties, if you apply if you consider the water contents in the flexible pavement design, increasing the water contents may result in more rotting or fatigue cracking. And the two figures below shows how it's going to happen. For example, if we consider a type of the subgrade soil or the aggregate base, they all have the saturated moisture contents. And once you have some waters from the top, it will be you will force down to the low levels, and then if there's any traffic or any vehicles moving on the surface of the pavement, you will actually cause some deflection to the subgrade layer, because the strength is reduced, the stiffness is reduced, and this will create the bottom up. This is the bottom up cracking, and by repeating the load, the crack will be formed from the bottom of the pavement structure to the surface of the pavement structure, and eventually will create a lot of crackings. It could be either longitudinal cracking or the transverse cracking, and it will make the entire pavement structure failed. So that's for the flexible pavement, and also it has some impact for the rigid pavement. The most common distress applied to the rigid pavement from the water contents is the mud pumping, the fatigue cracking. Here I'm going to give you a brief introduction about how the mud pumping is generated. The figure on the left is shows some typical mud pumping effect from the moisture contents, and you will observe the water coming from the bottom of the pavement structure. This is not a water from the rainfall. Instead, it's from the subground. It's from the groundwater under the pavement structure. And this usually happens for the rigid pavement. You know that for the rigid pavement, we will usually have the PCC slabs placed on the surface of the pavement structure, and for between different slabs, there will be some cracks, or if there are existing cracks inside the PCC slabs, you will also have the similar effect. And once there's a vehicle moving from one slab to another one, they will actually push the free water behind the slab or some fine particles behind the slab to move to the other side of the slab that the vehicle will move into. And then once the tire reaches to the next slab, then it will actually push the water back. And due to this kind of repeated movement of the water and fine particles, they will eventually ejected from the small cracks between or from the joints between the PCC slabs. And this will be the mud pumping effect for the rigid pavement. And this figure actually shows some more detailed mechanism about the mud pumping effect. And the most important is that there must exist some components, some aggregates with fine particles, and also they must have the water content, sufficient water contents in that area. And basically in the summary, the mud pumping will be due to the heavy traffic load from moving from two different slabs with the cracks, or the same slab with some cracks in between, and they will try to move the this kind of heavy load will move the fine-grained soils with the waters, and they will create a suspension for the PCC slabs. And then the increased pressure will move these fine particles and the waters out of the pavement structure. So basically, for the mud pumping effect, there will be some conditions. The first one is like the soil must have more than 45% of the particles passing through 0.075 millimeter sieve, and with the plasticity index higher than 6. So there will be more fine particles, and also it must have some free waters between the slab and subgrade. And this waters is held by these fine particles. And of course, it needs some frequent traffic load. The vehicles must move around the cracks a lot, or is very frequent during the unit time. And in order to solve the impact of the mud pumping, we have to, this is usually only happens for the rigid pavement. To solve this problem, we usually need to introduce some subbase layer between the rigid pavement, the PCC slab, and the subgrade. And with that, you will observe you will have the subbase to protect the load from the or try to transfer smaller load to the subbase layer or to subgrade layer. Then it will have the benefit to prevent the formation of the mud pumping. So that's this would be the general distress caused by the water contents to the rigid pavement and the flexible pavement. With that, I think I finished the introduction about the impact of the water contents to the highway subgrades. Do you have, for now, I want to pause for a while. Do you have any questions so far? And I highly recommend you to review the impact analysis of the water contents to the physical properties of the soils, and also try to review the standard test for the compaction. This will be very beneficial for you to understand or to analyze the potential errors in the field in the lab report. There might be some data that are not perfectly aligned with the model that we proposed, and this difference could be could potentially contribute by the inappropriate compaction or the inappropriate amount of the water contents. So just keep these two concepts in your mind when you're preparing the lab report. Okay, if you don't have any questions, I will go to the continue the introduction about the highway subgrade structure, but we will have more issues to discuss about the sub-base materials that we need to use and how we can improve the performance of the or the physical properties of those materials. So that will be the Note 7, the highway subgrade structure 3. So in this lecture, we will introduce a little bit more about the aggregates that we have to use for the sub-base and the base layers. There are also some type of the aggregates, but they have some specific requirements about the gradations, the distributions of the grain size, and also the emulsified materials that we need to use to improve their property. So this would be the three major layers that we have to consider behind the surface layer, the base layer, surface layer, sub-base layer, and subgrade. And we have discussed a lot about the subgrade materials. And for now, let's move to the upper two layers. So for the base layer, usually we will consider to use some granular base cores, and they will be applied to support the working load, and also it's used as the drainage layer to remove the water from the pavement structure, and also try to protect the first or try to remove the first heave effect. Just a moment, let me try to disable the timing. And for the selections of the granular-based cores, the granular-based materials, in Ontario, we usually need to consider the Ontario provincial standard specification. There will be the detailed instructions about how to select those materials. Basically, we need to consider three features: the very high internal friction angle, which is applied for these materials to support the heavy load without a significant deformation, the high permeability, which is applied for the drainage consideration, and the low contents of the fine, which is applied to prevent the freeze thaw effect, and also the potential swelling shrinkage potentials. In the United States, they're going to use the AASHTO manual to select the granular-based materials. Of course, in Canada, we also, for some provinces, they also use the standard from the AASHTO manual. Actually, the OPSS try to cite a lot of standards from the AASHTO. And in OPSS 1010, it defines three different materials: granule A, B, and M, which will be the most common granule-based cores applied in Ontario. For the granule-based cores, usually we can there will be several materials we can use. The first one we call it the unbounded granular aggregates. There could be some new aggregates that will be some crushed rock or gravel that we collect or we obtained from the from some mountains or from the in situ soil. And we also can use some recycled materials like the recycled asphalt pavement, which would be the pavement asphalt pavements that materials we have already applied for the highway design, but for the maintenance we remove them, and then this kind of material can be reused. Or we say that reclaimed bituminous materials are actually RAP and RBM. They will be the same term, just different names, but they represent the same materials. or we can use some recycled aggregate concrete. This is could be some recycled Portland cement concrete slabs, and this is usually comes from the rigid pavement. And there will be some other materials, some other industrial materials, such as the blast furnace slags. They can also be applied for the as the granular aggregates. And in the OPSS, the first define the gradation requirements for the granule base and the sub-base materials, which will try to identify the grain size distributions of the material. We are especially interested about the two materials, material A, granule A and granule B materials. This table actually shows the requirements about the different the percentage of different particles, different size of the particles. For example, for granule A, they should have all the particles passing through the sieve with the dimension of 26.5 millimeters. And then for 19 millimeters, it should be between 85 to 100 millimeters. And for some situations, it should be between 87 to 100 millimeters. And also, they want to have much. They won't have a very small amount of the fine particles, like the for the particles which were passing through the sieve with 0.075 millimeters should be less than 2 to 8%. And for the granular B materials, it's a little bit different. Usually there will be two types of the granular B materials depending on the gradation, the grain size distribution. And if you go to check the ranges, the potential ranges of the granular B materials, actually is wider. Most of the granular A material, the grain size distribution of the granular A materials will actually be covered by the granular B material. But there will be some difference. Even though for granular A and granular B materials, sometimes they may have the same grain size distribution, but usually the if one material has both the granular A and the granular B both has the grain size distribution forcing granular A, both granular A and granular B, but if the physical property is poor, then usually we will define them as the granular B material. The figure here actually shows the ranges of the granular size distribution that could be covered by A and B. For those grain size distribution within the blue lines, they will be granular A material. But for those within the red lines, they could be granular B materials. But as I just explained, there will be an overlap between the granular A and granular B materials. If there's one material forcing granular A, forcing the range of the granular A material, but the stiffness and the CBR is smaller, then probably we should assign them as the granular B materials based on the definition in OPSS 1010. So that's the typical way for us to identify the gradation requirements for the base and sub-base layer materials. And also there will be some physical property requirement defined by the manual. I think I'm missing one. The first physical property that we have to consider is called the Los Angeles abbreviation laws. And there are also some specific requirement about the values. And here I'm just gonna give you a brief review about the Los Angeles abbreviation test. And in this test, you will have very heavy steel balls, and you will put these steel balls. You put materials, the rocks in this machine, and then rotated them. With this kind of test rotated with a given number of times, then you will observe that these large aggregates, large rocks will be crushed into smaller pieces, and then we can measure the loss or the weight loss after the test. So basically, the LA loss is estimated as the mass difference before and after the test. So the mass original represents the mass of the materials before the test, which would be the original weight, and the mass after the test will only be the materials which can retain on the number 12 sieves. That is the sieve with the dimension of 1.7 millimeters. And using these two values, you can find out the percentage. And the table on the left actually shows some typical materials, which are the typical LA abbreviation loss for different type of the materials. Like for the for some sandstones, the loss could be as high as 60%. For limestones, it will be much smaller, it's 19 to 30%. And in the OPSS, we actually defined the percentage that we required for different materials. For example, for the granular A materials, the maximum loss should be 60%. But for the granular B, we do not have any specific requirement. And the second one is it's called the micro-Devo test. This one is it's different. It's quite similar to the LA abbreviation test, but the purpose is different. This test will use some much smaller drum and smaller steel balls. Those are all very small. You can compare them with the coin as in very small balls, and also you will put the aggregates in the drum and then rotate them for many times, and then after this test, you will observe that the aggregates will be polished instead of cracked into smaller pieces, and then we will try to measure the mass, the weight of these aggregates before and after the test. So this one is clearly very different from the LA abbreviation test. The LA abbreviation test will break the large aggregates into smaller pieces, but for the micro-Devo test, it will just make it smooth. So that's the requirement for the granular. For the first one, the coarse aggregate properties, and as you will know that you can try to do the area abbreviation test or the micro-Devo test to identify the properties of different materials, and then check whether they will be appropriate for the base or subgrade subbase aggregates. And the second one we have to consider is the it's called the freeze-thaw loss, and this is trying to reproduce the freeze-thaw effect to the aggregates or to the soils applied for the base and the subbase layers. And in the lab, it would be very hard for us to evaluate this kind of performance, like the frequent freeze-thaw effect. Instead, we will use the one test, which is called the sulfate soundness test, to evaluate the freeze-thaw loss. And this would be very similar to the LA abbreviation test, where we want to check the percentage of the weight loss before and after the test. The procedure of the sulfate soundness test is defined in the H2 test 104. And basically, you will try to generate some crystallization in the for the aggregates to simulate the freeze-thaw cycle. In the test, first you need to place the sample in the oven and separate them into the specific sieve size. Put them into different. You will first need to separate them into different into particles with different size, and then immerse the sample into the saturated solution of the sodium or the magnesium sulfate, and then let them remain in that solution for under the constant temperature for at least 18 hours, and then take the materials out of the solution and dry them in the oven to a constant weight. It depends on so the timing depends on how long or when you can make the weight constant, and then you have to repeat this cycle for 5 times. And after that, you're gonna wash the sample and remove all the salt and then let it dry. You also need to measure the dry weight. And then you have to determine the percentage of the weight loss before and after the test. And this percentage will be used for us to identify the freeze-thaw loss. And there will be some specific requirement about the freeze-thaw, the percentage of the freeze-thaw loss for different materials applied for the granule base and subbase layers. And these two pictures actually shows the effect before and after test. And before the test, you see that the surface of the aggregates is quite smooth. But after the test, you will see a lot of cracks along the samples, and this is it's actually applied to reproduce the effect of the temperatures, and temperature and the moisture contents, and it will make it will create the freeze and the thaw cycles during the winter and the springtime. So I think I can still cover one more topic. So the other thing that we can be applied for the granule base and subbase layer would be the bond based materials. With that we will apply some chemical materials or some binders to improve the property of the aggregates. So basically, the purpose of the bond based materials is improving the strength and reduce the moisture susceptibility of the soil. So there will be 2 types of the treatment for the material for the base course. One is the bituminant treated base course. Usually we will add 4 to 10% cutback or the emulsion to the soil, and usually the emulsions will be applied at the optimal moisture contents, and then we will compact them. And also we're gonna add an amount of the binder, the amount of the binder applied to these aggregates will also depend on the percentage of the fine contents of the soil. Usually with the larger percentage of the fine contents, we need to include more binders or the bituminers. But that's the common case. There will be some specific situation. The other things about the other kind of treatment is called the cement stabilization, and with that you will apply the either the Portland cement or the slag cement into the base course, the granule A or granule B or granule M materials, and the percentage would be varies from 3 to 16. This is kind of the percentage based on the weight. And in this kind of stabilization, we can also add some fly ash or the lime to further increase the resistance of the materials to the water contents. And I think I don't have enough time to finish all the about this topic. Okay, there will be 3 more minutes. Okay, so let me just try to finish one page and then let's see what kind of questions you have. So usually for the design of the pavement for the preparation of the aggregates for the subgrade for the base and subbase layers, we can use the cut back asphalt, emulsion asphalt, or the cement. For the emulsions, it could be the asphalt plus water and some emulsifying agent, and that's there will be different combinations about it. And for the cutback, that could be the asphalt, the volatile petroleum solvent, and this one can dissolve. The asphalt can dissolve in the solvent, and then combined with the asphalt, combined with the different aggregates, the granular aggregates. With that, it can increase the strength of the aggregates and also make it reduce the swelling potential of the aggregates to the water. So I think that's probably that's all about the bond-based materials, which we will have some specific chemicals to improve the property of the aggregates, so that they can better serve as the base and subbase layer course materials. Well, in the lecture tomorrow, I will continue this topic, and there will be some reclaimed materials which can also be used as the base and subbase layers. But we don't have enough time for that, so I'll just stop here, and let's see whether you have any questions about the lecture. Do you have any so far?
Hey, Professor.
Yes.
It's not about the lecture. It's about homework 1. It's due this Friday, right?
I think it's due Sunday.
It says October 1st on the actual assignment, but there's no assignment folder for us to upload anything to on Avenue.
Oh, I probably forgot to generate that, or I forgot to make it visible. So I'll make it visible so you can see it here.
Okay, awesome. Thank you.
Yes. I probably forgot it. It's the due on October 1st.
I think it says the 1st, but like we don't get pop-ups that say like when the homework's due until.
Okay. You already have all the informations for the first homework, so I think you have time to work on that. And I will create and make the homework visible so you can see it very soon.
Okay, awesome. Thank you.
Good. Okay. Any other questions? If you don't have any questions, that will probably be the all the materials today. And of course, we will have we'll continue we'll have the lab experiment next week. But not all the in-person students will be there. So if you have any concerns about schedule, contact me or the TA about it. Okay, I think that's all. And thank you very much for your time. And I really appreciate your effort in the class. And I will see you tomorrow for the continue this lecture.